Hi, and welcome to a project which I've just completed, which is to use Sonic Pi to play 14 Canons by J.S. Bach. They may think, well, that doesn't sound too much of a big deal, but in fact it turned out to be very interesting and using Sonic Pi in ways which I hadn't really done before. The Canons were only discovered in 1974 on the back page of a copy of Bach's Diabelli Variations, which had belonged to him and which he'd written, of course. And what he'd done was decided to take the first 8 fundamental notes from the Diabelli Variations and to use these as a theme for a series of canons. Now, he didn't write out the canons in full. There wasn't really room on one side of manuscript, but he indicated in them how the various parts were to be generated. And this raised my interest because I thought, well, if there are mechanisms to generate one part from another, then Sonic Pi ought to be able to do the calculations for this itself. The mechanisms involved things like inverting a tune. If, for example, you had a descending scale that went da 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 da, you could invert that and it would go da 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 da. And you could easily write a function, at least not easy, it turned out to be a bit harder than I had thought initially, write a function to carry out this inversion. The second thing that was done was sometimes to play the parts backwards. Well, that's very easy, because if you have a list of notes in Sonic Pi, you could just put dot reverse on the end of it, job done. Another mechanism which is used in the last of the canons was to have similar parts, but to have each part playing at half the speed of the previous one. Now again, that's not too difficult to do because you could take a series of durations and simply multiply each element of those durations by 2 or 4, depending whether you want to halve or quarter the speed. So I thought this would be a good thing to use for Sonic Pi. One thing which inspired me to do this was there is an absolutely superb YouTube video which shows these working, which you can find. You can see the address at the top there, and I'll put it in the notes underneath this video. And this video goes through and it shows things like this. If I move on a bit, take the first one. Here we are. Out there, and just play a little snippet of it, and you can see how it shows you the process which is done to start the thing going off. Well, I won't play it there, you can play it yourself on YouTube, but this inspired me to see whether we could actually produce this using Sonic Pi. Now, Sonic Pi is actually running here. It's got the screen set to low opacity, and you can see the first part of the screen here, which says a little bit about the round, but you'll notice that there's only one command that's executed, which is a run file command. Now, I've used the run file command because the entire program is quite long and far too long to fit into a buffer space in Sonic Pi. And so the way around that is to use run file and to specify exactly where the file is. It's called Bach Canons Final. I put a /rf on the end to remind me that I have to use it with a run file command. And if we move over here, we can actually see in a moment the if I find the right place, we can see the program. And you can see if I just scroll through it, that it is actually quite long, about 750 odd lines, although most of those lines are just used for generating a particular canon. To start with, it's very easy. For example, the first canon, if we move up again a bit, it starts about here, and those lines generate the notes, and these lines down here play the notes. So there's not an awful lot to it. I've got various put statements in which are going to print the Sonic Pi stream of notes on the screen. And also, you'll notice the picture we've got here, which I've already referred to, that is actually running inside a processing script. And we can see the processing script here. There it is. It's not very long. The main thing it does is to select from an array of pictures which are loaded in which one you want to display. And you simply have to put on that the pics and then the number P to C, which one you want to look at, and that will renew the background. And that is actually altered, and this is where the interesting bit comes in, by means of OSC messages. We get Sonic Pi to send an OSC message of the form /picture and then comma and then the number from 1 to 23, I think it is, of which picture you want to see. And you could see some being received here. In fact, its picture to see is 0 at the moment, which is this one here. And so at various places inside the program script, you can see one here, it says OSC picture 1, that will show the music for the first canon. And when we get to the second one, OSC picture 2. Some of the canons are longer and have more than one picture. It's very easy. We simply go to sleep for the number of deets we want, which occupies the first page, and then we ask for the next picture. And so that way we can actually display everything which is going on. So a very nice use of the processing script. Just to run through the other programs which I put on the screen here, just to show what's involved in producing a video like this. The video is actually being filmed on the screen using the Capto program. And there is a slight problem in that if we want to get the sound, we have to be able to record the sound output of Sonic Pi. And a program which enables you to capture this is a program which I've got here, if I just switch to it, which is called Audio Hijack. And this takes two sound sources in this case. It takes the output from Sonic Pi when it's running, and it takes the output of the internal microphone, which is switched in or out with a ducking device. That means that I stop talking, as I did then, it actually switches off, so you don't get a background, and you will only receive the output from Sonic Pi. That goes to my headphones that I'm listening to, but it also goes to an output device called Capto device, which is the recording device for the screen recorder. So that's how we collect the sound. Now, I've written the program so that it actually has on it the ability to play either MIDI or Sonic Pi. And if we look up at the top where there are some functions defined, there's a function here called define mplay that takes a note, a sustain value and a channel and sends out the MIDI command, MIDI N sustain S channel C. And if we look at one of the play commands, then this particular play command is going to use a routine called play. It's going to use play. It's going to play a list of a note and a sustain value, release and a pan setting, and it will only do that if a flag, M flag, is false. If that flag is true, it's going to use the mplay function instead to play that. So it plays MIDI if the flag is on, it plays normal Sonic Pi if the flag is off. And there's various routines which are used in the playing process. PL is one, PLD is another, and PL arrays is the third one, and the fourth one is PLSC. And again, that has a function to play MIDI or to play Sonic Pi, depending upon the value of this flag. Now, the reason that there are 4 different play routines is it depending on how the notes are actually produced. Sometimes we get just 8 notes and they are just repeated, and they are repeated a certain number of times, and that's what this PL routine is going to do. It's going to play the notes and reps is just the number of repetitions it has to do in going round through this list of notes. And the other thing which I need to say a bit about is the inversion. When you invert a scale, you actually do it by considering, or a piece of music, you actually do it by considering what are called the degrees of the notes which are played. A scale of G major, which is what this is written in, could be the symbolic notes colon G, colon A, colon B, colon C, colon D, E, F, back up to G. And those are the actual notes, but they are not equally spaced. G to A is a tone, A to B is a tone, B to C is a semitone, and equally F sharp to G at the end of the scale is another semitone. But the actual note degrees go 1, 2, 3, 4, 5, 6, 7, 8. And so what we do when we invert these is we simply subtract the notes from another number. If we subtract the notes 1 to 8 from 9, we will get 8, 7, 6, 5, 4, 3, 2, 1, which is the 1 to 8 scale inverted. So we do that inversion, and then we actually use the degree command to play the note that we actually want. And if I look down to the correct routine, which is this PSC one here, what we're going to do is to look at the degrees that we've got, and we're simply going to add those to the basic fundamental note, which might be G in octave 2, in which case 1 would be G octave 2 and 8 would be a G octave 3. And so by doing that we can actually carry out these inversions. Well, I'm not going to say any more about the program at this stage. It will be published and you will be able to have a look at it and to mull over what happens. Let's now just bring Sonic Pi to the front, and we do that by doing that. I'm going to make it slightly less opaque, like that, and we'll turn off the function relators. Do that just to get it out of the way, and then we'll start Sonic Pi playing, which we can do by the shortcut Command and R, because I've turned off the buttons at the top at the moment. So Command R, and here we go. It starts playing. A blurb about the program. Notice the page changed automatically from an OSC message. You see on the screen up here. Here we go. First one plays using built-in synths. Notice a repeat sign, so you can see it repeats the music. On to the next one. This time it switches to MIDI output, and you can see Ableton Live. There's two voices. One is on the left, the other on the right, and so you listen on headphones, which is the best way to do this. You can hear very clearly the two separate parts, one in each ear. See the rings down here that it's playing. Next one, two rings, one delayed 4 bytes before it actually 4 beats before it starts coming in. Time we invert them. Two bass parts, each one is in the verse of the other. As are the two treble parts. see the parts in note degrees printed on the screen on the right over here. Just the beginning of each part. These are then added to the bass note to get the actual note you play. So if you were in G3, the last note of part 3 there would actually be a G3. The 5 would be 5 notes up the scale higher. Notice in the audio hijack the Sonic Pi output showing as it's fed across to the output devices. I like this one where the notes are actually played one note displaced in each part. Now we're going to do the same thing but inverted. And that inversion is carried out automatically by Sonic Pi. I didn't write the parts out twice. Last one, we amalgamate the two separate halves together. Last one has rallentando added at the end, which is quite a difficult thing to do in Sonic Pi if all the notes are not synchronized for when you want to change speed. So I actually calculate them, and if you look carefully on the right hand side you can see some totals, 5.0685, which is the time for the last duration of the notes, and calculate the lengthening of the last few notes. And if you listen, I think you'll hear it works out quite nicely when we get to the end. This one also gets slightly louder as it approaches the end. And with that ending in rallentando, we come to the end of the 14 Canons by J.S. Bach. I hope you've enjoyed listening to this. I will also put it on SoundTube without me chattering over the top of it if you just want to hear what it sounds like. Thank you for watching.